I want to talk about the two problems that can be solved by dynamic programming with strings. So the first one I'm going to talk about is the longest common substring problem. So what does that mean? I have two strings S and T. They have M and N characters each. And I want to know what is the longest common substring. So a common substring is a substring that appears in both, that is a string that is a substring of both S and T. And I want the longest one. So substring, remember, means that the letters are consecutive in the original string S and T. A subsequence, on the other hand, can skip positions, right? So we talked about longest increasing subsequence problem before, and so that allows you to actually choose non-contiguous elements in your original string. But for substring, we're looking at contiguous chunk. So we can actually solve this by dynamic programming. And let me try to explain to you how that works. So we're going to define the function f with two parameters I and j. And I and j says that these are the locations that you're going to end at if you're going to have a substring. Okay, so let's just try to draw it out here. So S, let's say S is hello, okay, and T is help. Okay, so in this case, the first string has length 5 and the second string has length 4. So we're going to write the indices, of course, 0, 1, 2, 3, 4. And we can build a table f of ij. So I is this way. It's 0, 1, 2, 3, 4 correspond to HELLO. And then here it's 0, 1, 2, 3 correspond to HELP. Okay, so what is Fij? Fij is the length of longest common substring, and I must end at S at I and T of J. Okay, so let's look at the first row. What is the longest common substring that ends at H in the first string and ends at H in the second string? Well, it's 1. And the rest are all 0. Okay, this base case is pretty easy. If you only have one letter, only the first letter in each string, then either they're equal or they're not. Okay, similarly, the first column, the first letter in help, H, either matches H or it doesn't. Now, basically, anytime you see, so look at this entry right here. Okay, what's going on? E, this entry refers to E and E in both strings, so the two of these characters are the same, so of course it's at least 1. But you can actually extend this number and add 1 to it and becomes 2. So when the letters in the row and the column, right, so the row and the column here, okay, hang on. When the row and the column here, the two letters match, then you can just take the one that's diagonal to the upper left of you and add 1. Okay? What if it's not the same? So the next row, L and E, is not the same. So the longest common subsequence that ends here, longest common substring that ends here is just 0. Anytime you see mismatch letters, it is always 0. What about these two in the middle here? Okay, L and L, it's matched. So when it matches, we can look at the ones that are on the upper left, add 1 to it, and that becomes 3. Here, the next one, L matches. L and L also matches, right? And we can also say take this entry and add 1 to it. And this time the entry is 0, so when you add 1 to it, it's just 1. So if you look at this table and find the largest number, that tells you that the longest common substring has length 3. It ends at this location, right, in this string and in this string. And you go back 3 characters in each of the strings, and that's your longest common substring. Now, this table, of course, has quadratic size, right? The number of entries is basically the number of characters in the first string times the number of characters in the second string. So it's quadratic. And we'll go back to my slides. And so we have a base case that basically says if one of these strings is empty, then the longest common substring is 0. Otherwise, if the last 2 letters match, then it's just 1 plus the entry in the upper left. If the last letters don't match, it's 0. Okay, so the complexity again is quadratic, and it turns out that we can do much better for this problem, but this technique of using quadratic table is actually quite common. Now, in the assignment problem, I believe it's called vacation, you have to actually solve the same problem, except that instead of substring, you're looking for the longest common subsequence. And it turns out that you can do a similar thing. And I'm not going to expand too much more here because I have another video that talks about how to solve that problem. Okay, another problem it's very similar. It's the edit distance problem. What is this edit distance problem? Okay, so imagine that you have 2 strings, hello again. So string S, and then the second string could be welcome. What you want to do is to change S into T by doing 3 different operations. You can pick a letter and change it. You can pick a position and insert a character. I guess insert a letter. I'm using letter. And then finally, you can pick a position and delete a letter. Okay, so these are common operations that you can do when you're editing, right? And the goal is to change S to T with the minimum number of these operations. Okay, so what to do? How do you do this? So again, we're going to look at S and T, and I'm just going to draw sort of abstractly that you have a chunk of characters and you have a chunk of characters. Okay, and what I'm going to look at is what is the last letter. Let's say that they're both A. In this case, they're both the same, so I actually don't have to do anything. I can just cut this off, and I ask recursively, how do I change the first chunk of the letters and with the last letter drop into this one? If I can do that, okay, that's one way to change it. Okay, but I don't have to do that. I don't have to keep the last 2 letters like this. I can decide that no, okay, it's true that the last 2 letters are the same, but I'm going to insert a letter anyway. Okay, I'm going to insert a letter anyway so that this one match this one. In that case, I can recurse saying if the original string S can be changed to T, but with the last letter of T dropped. And what is the minimum of operations that I need to do that? And so what that means, if this original string has length n and this has length m, I'll be looking at f of n, but m minus 1 plus 1 to indicate that I've added this one letter here. Okay. Okay, similarly, instead of inserting, I can decide to delete. Okay, so I can say, even though they match, I can say delete this one. So in one operation, my string now here is shorter, and I still have to take this shorter string to convert it to the entire T. And if that's the case, then my recurrence would be this. Okay, I shrink the first string and not the second one. And so basically there's three one more possibility. Okay. If the last two letters don't match, then another possibility is to actually change this letter into an A. And now the last two letters match, and I can recursively try to figure out how to transform the first part of S into the first part of T with the last characters removed. So if you get all of that, the recurrence here is basically like this. So f of ij will set it to be at the distance, okay, of the first I characters of S to the first J characters of T. We will, of course, want to compute F for the entire string M and N. Okay, so the M letters in the first string, N letters in the second string. Okay, if the second string is empty, but the first string is non-empty, then the only thing you can do is just delete all the characters one at a time. So if you have I characters, you want to get it empty, you just delete I times. Similarly, if the first string is empty, but the second one is not, the only thing you can do is insert exactly J times. If it's not the boundary case, what are you going to do? You're going to look at this, whether the last two characters match, the last character of each string match. If they match, this is 0. So this is a Boolean expression that evaluates 1 or 0. If they match, it's 0, so you don't have to do any changes. And you can just chop off the last character of each string, recurse. If they are different, you can do one operation to change the last character to make them the same, and again chop them off and recurse. Or you can insert a character, which we just explained. That means you don't shrink the first string, but you shrink the second one. And deleting is the opposite. You shrink the first string and you don't shrink the second one. And basically you compute this table. So what does this table look like? You're going to have this table that's index F. This is going to be indexed by I. This is going to be indexed by J. And then, I guess my J is too high. So this is indexed by J. This is going to go from 0 to M this way. The entry that you want at the end for the final answer is this one. You're going to fill this, the base case is here, the first row and first column. And then every element that you're trying to fill, it's either this one plus 1, this one plus 1, or this one possibly plus 1 or plus 0, depending on whether the last characters are matching. So you can use a recurrence, top-down dynamic programming, or you can just loop through this table one row at a time, because at every step, when you compute an entry, you're always referring to something that's above you, to the left of you, or diagonally on top of, to the left of you. So if you go one row at a time from left to right, every time you're computing some entry, all the things that you need to compute that you're using, you're referring to are already computed. And the complexity is, of course, bigger of m times n, because your table has this size, right? So that's another classic example where you can build a quadratic table to solve problems by matching the last character and then recurse.